Non-metals, generally non-metals have properties opposite to those of metals. So earlier when I explained the periodic table, I said metals have certain properties, non-metals have properties opposite to that. So that is what we are going to look at. There are non-metals which occur as native elements as well as compounds of other elements. So if we take examples, there is sulphur, which is a non-metal. Then we have carbon, that is also a non-metal. These exist in different forms as non-metals in nature. So these exist as native elements. So there are other non-metals that can exist as compounds, and some non-metals exist as both compounds and native elements. For example, sulphur, although it exists as a native element, there are sulfates which are compounds. So we can have sulfates. Similarly, carbon is present as compounds. So carbon as oxides, oxides of carbon. Then you all know that carbon is present as carbonates. Likewise, we can talk about many different compounds that are made of non-metals. So these are in the form of compounds. So non-metals can either exist as native elements or as compounds. Some non-metals occur in the solid state, while some others exist in the liquid state and gaseous state. If we take different elements, for example, oxygen, nitrogen, these are even fluorine, they are all in the gaseous state. Whereas if we look at elements like bromine, it is a liquid. And elements like carbon, sulphur, they are all solids. So unlike metals, which are mostly solids, non-metals can be gases, liquids or solids at room temperature. Okay students, now we will discuss the physical properties of non-metals. Physical properties of non-metals. So students, you all know non-metals have properties opposite to that of metals. So if we take metals, they have a luster, but non-metals do not have a luster. So the first property is that they do not have or do not show luster. That means they don't have that metallic shine. They do not have the sonorous nature, or they don't make a sonorous sound. So the next property is no sonorous sound. And also we saw that metals were ductile and malleable. But here non-metals are not ductile or malleable. If we look at non-metals, they are brittle. You can't hammer them into sheets or draw them into wires. That means they are not malleable or ductile. But if you drop them, they break. So because of that, they are brittle. Non-metals are brittle in nature. They can break They are brittle in nature. They can break easily. Can break easily. And also, unlike metals, non-metals are not good conductors of heat and electricity. Not conductors of heat and electricity. But if you take carbon in the form of graphite. Graphite is what we have in the pencil lead. And you all know graphite is used as an electrode. So graphite can conduct electricity easily. So graphite is a good conductor. Except carbon, graphite. This is a good conductor of electricity. And also we talked about the brittle nature and not having a shine. The same way carbon exists in another form, which is diamond. Although we expect diamond to have the same properties, it's very strong. So diamond is not brittle. At the same time, diamond has high refractive index so that it can refract light nicely. That is why diamond is very valuable. Okay, so here we have another exception. Diamond is very strong and not brittle. Also, it has high refractive index. Non-metals are relatively low in density. Relatively low density. But here also there is an exception. Diamond that has high density. Very high density. Okay, students. So these are the physical properties of non-metals. Now we will discuss some of their chemical properties. Chemical properties of non-metals. Non-metals form negative ions or anions. So metals formed cations. They lost one electron and formed cations or positive ions. Whereas non-metals usually take up one or more electrons and therefore they form negatively charged ions, which are called anions. For example, if we take chlorine, chlorine can take up one electron and form a 1 negative ion. This is called a chloride ion. So that is an anion. Many oxides formed by nonmetals with oxygen are acidic. So the oxides, if you can remember students, recollect what we discussed with metals. Yes, the metals form basic oxides. So the nonmetals are opposite of that. They form acidic oxide. So for example, when sulfur burns with oxygen, it forms sulfur dioxide. Sulfur dioxide. This is an acidic oxide. And usually oxides of nonmetals exist in their gaseous state. For example, again, sulfur dioxide is a gaseous oxide. Carbon dioxide is a gas. Nitrogen dioxide is a gas. So like these, most of the oxides of nonmetals are gases. The oxides easily dissolve in water and form acid. If we take sulfur dioxide, it dissolves in water and forms acid. Sulfur trioxide dissolves in water and forms sulfuric acid. Carbon dioxide can dissolve in water and form carbonic acid. Nitrogen dioxide can form nitric acid. So most of these oxides dissolve well in water and form most common acids. So as example, we can say nitric acid and sulfuric acid. Okay students, so you have understood the physical and chemical properties of nonmetals. Now we will look at some examples of nonmetals and their properties. So some non-metallic elements, as an example, we will consider nitrogen. Nitrogen exists as a diatomic gas in nature. So in the environment, in the atmosphere, if we look at the composition of air, there is about 78.1% of nitrogen. So nitrogen exists as free diatomic gas in the atmosphere. And if you look at the atmosphere, about 78.1% is nitrogen gas. And we said it is a diatomic gas. That means it exists in the form of N2. The same goes for air in the soil. So in soil, you know that is soil air and soil water. And the soil air also contains nitrogen. I will write that as well. Soil air also contains nitrogen. If we look at the living organism, we have discussed in the first lesson, out of the biomolecules, proteins, amino acids and nucleic acids contain nitrogen as a constituent element. So therefore, nitrogen is present in animal and plant proteins and amino acids. So, nitrogen is present in plant and animal proteins and amino acids. And also it is a constituent of nucleic acid. It is a constituent of nucleic acid. In addition to that, nitrogen is present as compounds in soil. There are three main forms of nitrogen: the nitrides, nitrates, and ammonium compounds. So, nitrogen is present in soil as nitrides, nitrates, and ammonium compounds. So, as you can see, nitrogen is a free diatomic gas which is present in the atmosphere as N2 gas. At the same time, it's present in the soil in different forms in plants and animals, and also it's a component of the soil air. Now, we will discuss the physical properties of nitrogen gas. Nitrogen is a diatomic gas. It is colorless and odorless. So, the first physical property is that it is a colorless and odorless gas. And also, nitrogen is slightly soluble in water. It is slightly soluble in water. So, those are the physical properties of nitrogen gas. Now, we will look at the chemical properties. Chemical properties of nitrogen. Nitrogen is a non-supporter of combustion. So, if combustion is taking place, if there is nitrogen there, it doesn't support combustion. That is why even though there is lot of combustion, burning taking place in the environment, the amount of nitrogen does not change because it is a non-supporter of combustion. It is a gas of very low reactivity. Very low reactivity. That is why again it is present in very high percentage in the atmosphere. About 78% is nitrogen because of its low reactivity. But nevertheless, at high temperatures, nitrogen gas reacts with nonmetals such as oxygen, hydrogen, carbon and silicon, as well as metallic elements such as magnesium and aluminium. So, at very high temperatures, nitrogen can react with both metals and non-metals and can form compounds. So, nitrogen with oxygen, nitrogen dioxide. Hydrogen with nitrogen, ammonia. Likewise, with carbon and silicon also, it forms compounds. With metals, when we looked at properties, when we were discussing properties of magnesium, you saw the magnesium strip having white and black color layer on top of it. That is due to the oxide and the nitride layer. So, this nitride layer, the black color layer, forms due to the reaction of magnesium with nitrogen. Similarly, aluminium also can react with nitrogen. When sent through a strong electric arc, so the strong electric arc provides very high energy for reaction. Nitrogen combines with oxygen in the atmosphere to form unstable nitric oxide gas. So, nitrogen, when you supply a lot of energy, an electric arc can react with oxygen and form a type of oxide called the nitric oxide. This is also a gas, and this gas reacts further with oxygen in air to form an acidic gas, which is nitrogen dioxide. We discussed about nitrogen dioxide before. So, this is a very acidic gas, and this process takes place during lightning. So, normally when there is lightning, there is very high energy and electric charges. So, lightning provides this strong electric arc which makes the nitrogen in air to react with oxygen, forming nitric oxide, and that gets further oxidized and forms nitrogen dioxide. If you think of it, students, this nitrogen dioxide can dissolve easily in water. So, usually during rainy time only there is lightning. So, due to lightning, if nitrogen dioxide is formed, that can dissolve in rainwater and it can become like an acid rain. The water will become acidic. So, that could be a problem, a harm to the environment. Under special conditions, nitrogen gas reacts with hydrogen gas to form ammonia gas. So, nitrogen and hydrogen react to form ammonia gas. This reaction is used in industries. So, you can say industrially ammonia is manufactured by this method. So, this is an industrial process that is used to produce ammonia. And the ammonia that is prepared by this method is used as a raw material to produce nitrogen containing fertilizers and explosives. So, what do? They react nitrogen and hydrogen under special conditions, and ammonia will be formed. From that ammonia, it can be used as a raw material to produce other substances which are fertilizers or explosives. As an example for nitrogen containing fertilizer, we can talk about urea. Urea is a nitrogen containing fertilizer that can be produced from ammonia. When heated, nitrogen gas reacts with metals like magnesium to form metal nitride. We have discussed this before. On the surface of magnesium, you will see magnesium nitride, which is a black color compound. So, that is a reaction that happens when magnesium is heated, it reacts with nitrogen. Or when there is high energy provided, this reaction will take place. So these are the chemical properties of nitrogen. Now we will see how we can use nitrogen. Uses of nitrogen gas. Nitrogen gas is used to produce ammonia in the industrial scale. Chemical fertilizers are produced using ammonia and other nitrogen compounds like explosives. So, nitrogen is a raw material for the production of ammonia, which becomes a raw material for other industries. Since it is an inert gas, when we say inert, that means they are very less reactive. They exist as diatomic gases and they are very less reactive. It is used to fill electric bulbs and thermometers. Inside electric bulbs, the tungsten filament has to become very hot. If there was air inside it, that tungsten filament can react or burn. To prevent that, they fill the bulb with nitrogen gas. The same goes for thermometer. The space is filled with nitrogen gas because of its low reactivity. When making electronic devices, nitrogen gas environment is used. When we say nitrogen gas environment, in a certain area there can be nitrogen inside which the making of the electronic device takes place. So again, it provides an inert environment, a less reactive environment for the production of electronic devices. When storing some substances, nitrogen is used as a blanketing gas. So like how we cover things with a cloth or with a paper, wrap it up. Here they use nitrogen gas as a blanket, like a cover around certain substances. Wherever you need to have less reaction or prevent reaction, nitrogen is used as a blanketing gas. When packaging milk powder, nitrogen is used. You all know different milk powders, they come in packs. And if there was air inside the pack, the milk powder can become stale quickly. To prevent this, they fill the space with nitrogen gas. So the milk powder is retained fresh for a long period of time until the expiry period. Liquid nitrogen is used as a coolant. So here we are using liquid nitrogen as a cooling agent. By reducing the temperature of nitrogen gas, we can condense it and get the nitrogen liquid. This has a very, very low temperature. Therefore, it can be used as a coolant. In special equipment, we can use it as a coolant to prevent or reduce the heat that is generated or to cool down that device. It is also used to fill vehicle tires. So because again it is an inert gas, it's less reactive, it can be used to fill vehicle tires. So we have discussed many uses of nitrogen. It is a diatomic gas, it's a non-metal and it is less reactive. So because of these, it has many uses. Now we will look at another example of non-metals. Sulphur. This is another example of non-metals. So as you know, non-metals have certain properties. This is the sulfur that exists in nature and this is one of its forms. Before we look at the physical properties, we will just try to remember and recollect the position of sulfur in the periodic table. Try to recollect the position of sulfur. Yes, it has the symbol S and the atomic number 16. So, what do we need to write? We need to write the electronic configuration 2, 8, 6. So, from that, we can find the group and the period of sulfur. Group will be what? The number of electrons in the last shell. So, it's going to be group 6. And what is the period of sulfur? Yes, there are electrons in 3 energy levels. So, it will belong to period 3. So, the position of sulfur in the periodic table is group 6, period 3. And if we look at the different forms of sulfur in nature, it can exist as native element. So, if we look at the natural form, it can be in the form of a native element. This native element is of different types or different forms we can say. When we say forms, these forms are called allotropes. Allotropes are naturally existing forms of an element. Under this, there are 2 main types of allotropes. The crystalline form, which has crystal structure, that is particles with sharp edges. And the amorphous form, which is a powdery substance. So, if we look at the allotropic forms of sulfur, the first type is crystalline structure, crystalline form. What you see in the picture is a crystalline form of sulfur. So, this exists as yellow color, brittle, that means it can break easily, crystalline solid. That is one allotrope of sulfur. The same way it can exist in the amorphous form. The amorphous form is a white color solid. So, it can be an amorphous form that is going to be a white color powder or solid. So, those two are 2 main types of allotropes of sulfur. At the same time, sulfur can exist as compounds in nature. So, if we look at examples of compounds, sulfates and sulfides are a few examples. In addition to that, sulfur is present in some of the amino acids. This we have discussed in the first lesson. So, amino acids make up proteins. Therefore, sulfur can be present as a constituent element in some amino acids and proteins in plants and animals. So, that is another form. It can exist as compounds. And for compounds, we can take the examples sulfates, sulfides, then some amino acids and proteins. Okay, students. So now we have looked at how sulfur exists in nature. And as you know, this is a very good example of a non-metal. So it will show properties of non-metals. Now we will look at the physical properties of sulfur. Physical properties of sulfur. So as you know, students, since sulfur is a non-metal, it does not conduct electricity or heat. So it's a poor conductor of heat and electricity. It is a poor conductor of both heat and electricity. And sulfur does not dissolve in water or any polar solvent, but it dissolves in organic solvents. That also it dissolves slightly in organic solvents, but it dissolves very well in carbon disulfide. So here the second physical property we can say does not dissolve in polar solvents. Dissolves well in carbon disulfide. And the chemical formula of carbon disulfide is CS2. Carbon and 2 sulfur atoms. So we call it carbon disulfide. So students, these are the physical properties of sulfur. Now we will move on to the chemical properties of sulfur. Sulfur burns with a blue flame in air and forms sulfur dioxide gas. So if we write that as a word equation, you can show it as sulfur plus oxygen, that is the component that is going to react from air to give sulfur dioxide. So this again, from the name you can see sulfur and 2 oxygen atoms, dioxide. And you are already familiar with this sulfur dioxide. You would have heard about sulfur dioxide in general. This is a gas that is very, very acidic and it can cause acid rain. So this is a very acidic oxide of sulfur. So sulfur burns with a blue flame. You can identify the yellow color crystal sulfur. When it burns, you can observe a blue color flame and the result will be sulfur dioxide, a gas. The second property is when heated with sulfur, many metals form the metal sulfide. So metals can react with sulfur and form the sulfide. So for example, if magnesium reacts with sulfur, it will form magnesium sulfide. So that is another chemical property that you have to remember, students. And sulfur, being a non-metal, reacts with many metals. That is something that you have to remember. So you have understood the chemical properties of sulfur. Now we will do an activity to observe the chemical properties of sulfur. The activity is burning sulfur in air. So for that, we will need these materials and equipments from the lab. First, we need sulphur. So usually, we have the yellow color crystalline form of sulphur in the lab. So we will be using that for the activity, and we will need a spoon to heat the sulphur, and also you will have to have a wooden handle. Here it is better if we have a wooden handle or a plastic handle that does not conduct heat, so that you can easily hold the spoon to the flame. Next, we will need the Bunsen burner. So this is a very simple activity where we take a very small piece of sulphur crystal in the spoon and we hold the spoon over the flame of the Bunsen burner. But students, you have to remember the product of this activity, which is sulfur dioxide gas. It's harmful to the environment as well as harmful to people. So therefore, we don't do this in the laboratory normally. But here, for you all to observe the color of the flame and what happens to sulfur, we will be doing this activity, but with the smallest minimum piece of sulfur, so that we reduce the harm to the environment. So now I will summarize the procedure of this activity. The method. So first you have to take a small piece of the sulphur crystal into the spoon. Then the second step, you hold the spoon over the Bunsen flame. Hold the spoon over the Bunsen flame. So when you hold it like that, you can see what happens to sulfur and how it burns. So now that you know the procedure of this simple activity, we will go to the lab and do this activity. Okay students, now we will do the activity of burning sulfur in air. As you know, when sulfur burns with oxygen, it produces sulfur dioxide. That is a harmful acidic oxide gas. So because of that, normally we are not supposed to, or we avoid burning sulfur in oxygen and producing sulfur dioxide, which can be harmful to the environment as well as somewhat uncomfortable for the person who is doing the activity. But here, for you all to understand and see the observation, I will be doing this activity using the minimum amount of sulfur possible. So as you can see, sulfur is a non-metal that is stored in the lab inside a plastic bottle. When you take out the sulfur, you can observe it clearly. It is a yellow color crystalline solid. Here you can see the crystalline nature of sulfur, and make sure that you don't touch any of these chemicals directly with your hand. And also, since I am going to use the burner and heat or burn sulfur, I will be using protective glasses or what we call as goggles as protection for my eyes. If you are able to use gloves, that would be also better. I can wear the goggles over my spectacles. Right. So, I'll be using this spoon which has a handle that will not conduct heat to burn sulphur. So, I'm going to use this spoon to heat sulphur. This has a handle that does not conduct heat. So, it's easy for me to hold it to the flame, and I will select the smallest piece of sulphur with which you can observe the changes clearly. Now, I will hold it to the flame. Observe the changes carefully. You can see the yellow color crystalline substance. With time, if you observe closely, you can see at the bottom the sulphur becoming a liquid, and the liquid is dark brown in color. Now, sulphur has completely liquidified. Now, it will start burning. You have to observe closely and clearly to see the change. You can see now sulphur is turning dark, almost blackish in color. Then it will start burning. If you look closely, students, you can see the blue color flame. You have to look closely near the spoon around the sulphur area. You can observe the blue color flame with which sulphur is burning. That is how sulphur burns in air. It burns with a blue color flame and completely gets converted to sulphur dioxide. Okay, students. Now you observed all the changes that took place when we burned a small piece of sulphur in air. Now recollect what you saw during the activity. Those are going to be your observations. What were the observations? Yes, first the sulphur melts and forms a light brown colored liquid. So the first observation is sulphur melts and becomes a light brown liquid. Then what happens to this light brown liquid? It turns dark brown in color. It turns dark brown in color when you keep on heating it. Then afterwards, the sulphur starts burning. Then you can observe the blue color flame. Burns with a blue color flame. Here, if we use a larger amount of sulphur, larger quantity, you can also get the odor, which is an irritating odor. But since we used a very tiny piece, even I could not get the odor that much. So that means it's not very harmful to the environment. So these are the observations that you need to remember. Mainly that sulphur burns with a blue color flame. So from this activity, we can conclude that sulfur burns with a blue color flame. And what do you get as the end product? Yes, it is the sulfur dioxide gas. So therefore, we don't have anything remaining in the spool. So we can say sulfur burns with a blue color flame and produces sulfur dioxide gas. So this is the conclusion that we get from this activity. So although burning sulfur is not good for the environment, sulfur can be useful in many ways. So now we will see the uses of sulfur. Uses of sulfur. You know, students, in the laboratory we have certain chemicals that we use very commonly. And one of those chemicals is sulfuric acid. This is a common laboratory acid. The chemical formula will be H2SO4. This we will discuss towards the end of the lesson, how to write chemical formulas. But I have been introducing different chemical formulae throughout the lesson. So sulfuric acid is something that you need to remember, H2SO4. So this can be used in the lab. It can be used for batteries, and there are many other uses. We can also use sulfur for vulcanizing of rubber. When we say vulcanizing of rubber, normally, you know, students, rubber can be obtained naturally or it can be produced synthetically. And this rubber has many good properties. That is why we use it to produce many products. The normal rubber cannot be used for a very long period, and also it cannot withstand very high pressure. So in order to modify this and make it better, what we do is we burn or we react rubber with sulfur. When rubber is heated with sulfur, it reacts and forms the vulcanized rubber, where sulfur combines with rubber and makes it more stronger and more durable and long lasting. So that is the reason for vulcanizing rubber. For that we use sulfur. To make calcium and magnesium sulfide. When we started this topic, we saw that sulfur exists as compounds, and sulfates and sulfides are a few examples. And magnesium and calcium sulfide are needed for many purposes. To produce them, we use sulfur. To produce paints containing sulfides, then solvents like carbon disulfide, sulfur dioxide gas, matches, crackers and gunpowder. So there are many substances that can be produced using sulfur. Paints containing sulfur, then sulfides, as we said, magnesium, calcium sulfide and other different sulfides, carbon disulfide, which dissolves sulfur itself. So that is also produced using sulfur. Then sulfur dioxide gas for different purposes like producing sulfuric acid. Then matches, the matchstick that we use for household purposes. Crackers, the lighting crackers, and gunpowder. used in the production of wine, beer and medicines. So in these two processes, production of wine and beer, they use sulfur, and in certain medicines. Usually the antifungal cream, they contain sulfur. So for those types of medicine production, we use sulfur. And used as a fungicide. When we say side, that means we need to destroy a microorganism or some organism. So here, fungicide means to destroy fungus. To produce fungicides, we use sulfur. So as you can see, students, sulfur exists in different forms, that is the allotropic forms. It shows properties of nonmetals. It can burn in air and also it is useful in many different ways. So that was an example of a nonmetal. Now we will look at another nonmetal that is used in our day-to-day life. This nonmetal is carbon. So from the picture, you can see there are two types of carbon. Before I go into that discussion, we will just recollect the atomic number, electronic configuration and the position of carbon in the periodic table. So if you can remember, students, I am sure you remember carbon has a symbol C. And you can remember it was 12,6 carbon. So atomic number 6. If we write the electronic configuration, 2, 4. So 2, 4 means what is the group? Yes, it belongs to group 4 in the periodic table. And what is the period? Yes, it belongs to period 2. So the carbon element has atomic number 6. So electronic configuration, group and period is something that you can identify. You can remember, students, carbon shows another property related to its mass number. What is it? Yes, it shows isotopic forms. So carbon has atoms with the same atomic number, so the same element, but different mass numbers. Okay, so those are the properties that you already know. Now we will discuss some more properties of carbon. If you look at the picture, you can identify this is a diamond and this is graphite. Graphite is what we use in pencil leads and as electrodes. Yes. So these are two naturally existing forms of carbon. So that means carbon can exist as native element. Again, it shows allotropic forms, and under that there are crystalline forms and amorphous forms. At the same time, carbon can exist as compounds in nature, like carbonates. So if we first look at the native element, there are allotropes. Native element exist as allotropic forms, and out of these allotropic forms we have the crystalline carbon, crystalline form. Under that we have both diamond and graphite. The two crystalline forms are diamond and graphite. So when we say crystalline form, you can see that they have sharp edges and shiny nature. At the same time, carbon exists as amorphous forms. Amorphous forms. As examples, we can take coal, charcoal, and lamp shoot. So those are the amorphous forms of carbon. Coal, charcoal, and lamp shoot. When we burn something, the substance, the black color residue that remains can be either coal, charcoal, or lamp shoot, depending on what we are burning. So this is an introduction to carbon. Now we will discuss the physical and chemical properties in more detail. The physical properties of carbon. Physical properties of carbon differ according to the allotropic form of carbon. So it depends on the allotropic form of carbon. In the first picture itself, you saw diamond and graphite. You know that they are totally different. Diamond is very strong. It can refract light. It is a crystal. And whereas graphite is a black color crystalline structure and it is brittle. So within those two allotropic forms itself, you can see the difference. They have different properties. Most of the allotropes of carbon are black in color. The exception is diamond. Except diamond, the other forms of carbon are black in color. So except diamond, the other forms are black in color and exist in the solid state. So all the allotropes exist in the solid state, but only diamond has the crystalline nature. All the others are black in color. Their density is relatively low. Again, their density is relatively low, but again, diamond is the form with highest density. So, as you can see, although diamond is a form of carbon, it's very strong, not brittle, and also it has very high density. All the other forms have relatively low density. Diamond is a poor conductor of electricity. Diamond is a poor conductor of electricity, but graphite is a very good conductor of electricity. Again, a difference between the types of allotropes. Because graphite is a very good conductor of electricity, we use it as electrodes. Charcoal can absorb gases. The different types of gases can be absorbed by charcoal. Therefore, it can be used as a filter. So, this is a special property. Charcoal can absorb gases. So, students, these are the physical properties of carbon. Let us discuss the chemical properties of carbon. Chemical properties of carbon. Carbon is an element of low reactivity. So, it does not react that much. That is why both diamond, graphite and the other forms of carbon, charcoal, coal, they can remain in the atmosphere over a very long period of time as they are, because they are very less reactive. It combines with oxygen at very high temperatures. but not react with substances like acids, bases and chlorine. So, carbon can only react with oxygen at very high temperature and form carbon dioxide gas, whereas it does not react with substances like acids, bases and chlorine. Chlorine is a gas and that is also a non-metal. Amorphous forms like charcoal react chemically. So, amorphous forms can react chemically. Charcoal can be used in chemical reactions, but not carbon, diamond and graphite. When strongly heated and ignited, charcoal reacts with oxygen to form carbon dioxide. So, here we need to provide strong heating, that is to very high temperature and ignited. If it starts burning, then charcoal will react with oxygen to form carbon dioxide. So, that also needs very strong conditions for reactions. At high temperatures, carbon reacts with calcium oxide forming calcium carbide. So, carbon reacts with calcium oxide forming calcium carbide. Calcium oxide is an oxide of calcium and that on reacting with carbon can form calcium carbide. Calcium carbide is a chemical substance that is also useful to us. So, this is again at high temperatures. So, students, you have to remember these are the chemical properties of carbon. And remember, both the chemical and physical properties depend on their allotropic form. So, they can be extremely different as well. With that in mind, now we will discuss the uses of carbon. Uses of carbon is given based on the allotropic form. So, in this table, you can see we have the form of carbon and the uses. The first type is just the amorphous carbon. Since it is black in color and amorphous in nature, this is used to produce black color ink. Amorphous carbon is used in the production of black color ink and also for vulcanizing of rubber. The second type of carbon, coal, is used as a fuel. We use coal for burning and production of energy. Even for the power plants, we can use coal as a fuel material. So, coal is useful as a fuel. Then we have graphite. This is a crystalline form of carbon. This is used in making pencils. The lead of the pencil that you use to write, the black color writing is due to graphite. So, that is again carbon. Making electrodes of electrochemical cells. So, as we discussed before, out of the different allotropes of carbon, graphite is a good conductor of electricity. The others do not conduct electricity. So, therefore, this is used as electrodes. Used as a lubricant. When we say lubricant, this is a substance that is used to reduce friction. For example, if there is a machine part, if it is corroded or if it's too tight, it starts making screeching sound. So, to reduce that, we apply oil. Their oil is a lubricant. The same way, we can use graphite as a lubricant. Diamond, the next form of carbon. This is used in making jewelry. Because carbon is very strong, the diamond form is very, very strong. It has a very high refractive index. It has special properties that makes it very valuable in the production of jewelry. So, diamond jewelry are very attractive because of its high refractive index. Then it is used to cutting glass and gems. Because diamond is very, very strong, the instrument that is used to cut glass and gems contains diamond in it. The strength of diamond is used in cutting these materials. Used as pivots at points in machines that are subject to wear away. So, when you have a machine where there is continuous movement, say like a wristwatch where the hands keep on moving, then it can undergo wear very easily. So, the pivot, if it is placed on a small piece of diamond, this wear can be reduced. It can last for a longer period of time. Again, because diamond is a very strong material. So, used as pivots at points in machines that are subject to wear away. Those are the uses of diamond. Then we have charcoal. Charcoal is used for absorbing gases. So, we discussed before also, charcoal has the absorbing property. So, it's used in filters. Charcoal is also used for purification of water. So, when we say water purifiers, those are the normal filters that we use in households. If you have observed someone cleaning a filter, you might have seen this charcoal filters. Maybe a cylindrical structure that contains the black color charcoal. Since charcoal has the ability to absorb impurities, it is very, very useful in purification of water. Not only the household filters, even large scale water purification, charcoal can be used. Carbon fibers and carbon tubes. Those are another type of carbon. And this is something that is familiar to you all because you have learned nanotechnology in grade 9. In that, you are familiar with carbon nanomaterials. And these two, the carbon fibers and carbon tubes, are nanomaterials. So, they are used to produce goods reinforced by nanomaterials. Carbon fiber is very light and it is very strong. So, that is the purpose why carbon is very useful in nanotechnology. Carbon fiber is very light and it is very strong. Therefore, it has a very wide usage. So, students, with this, we have finished the discussion on uses of carbon. And also, we have looked at different types of metals and non-metals. Now, we will look at the next type of elements, that is the metalloids. Some metalloids. Try to remember the periodic table. In the periodic table, the left side of the periodic table mainly contains metals except hydrogen. On the right side, we have the non-metals and the noble gases. In between the two, there was a stepwise pattern. This contains metalloids. And these metalloids have properties between metals and non-metals. As an example, we will look at silicon first. So, if we recollect the position of silicon, silicon is present in group 4 and period 3. So, silicon is present in group 4, period 3. That is the position of silicon. If you look at this picture, you can see it is a black color, shiny, solid material. Now we will look at some properties of silicon. Except oxygen, silicon is the most abundant element in the earth crust. So, if we take the earth crust, it is made up of many compounds and elements. Out of those, if you look at the percentage of each element, silicon is the most abundant element next to oxygen. As compounds, silicon occurs in both crystalline and amorphous forms. So, there are compounds of silicon which are crystalline. For example, quartz and other gems like emerald are crystalline in nature, and clay is the amorphous form of silicon. So, here you can see quartz, sand and gems such as emerald are crystalline silicon compounds. Quartz is a substance that is used to make materials in the lab. Quartz is similar to glass but doesn't break easily. It can be used for withstanding high temperature and as very useful materials in the laboratory. Then sand is the normal sand we have that contains silicon compounds, and also precious gems like emerald. It contains silicon compounds. And clay is the amorphous silicon compound. As you can see, students, silicon is present in nature as both crystalline and amorphous forms. And also it is the most abundant element in the Earth's crust. If we look at the melting point of silicon, it is 1410 degrees Celsius. That means it has a very high melting point. Therefore, it exists as a solid in room temperature. So, those are some of the properties that you need to remember. Now, we will discuss the uses of silicon. Uses of silicon. Silicon, since it is a metalloid, it can conduct electricity to a certain extent. But under certain conditions, it becomes a very good conductor of electricity. Therefore, we call it a semiconductor. And these semiconductors are very useful in electronics, in making electronic equipment. So, used in making transistors and diodes. These are electronic equipments. You will be learning about these equipments and their functions in later stages. Now, for now, remember, silicon is useful in making transistors and diodes, which are electronic equipments. Used in making solar cells. And you know the function of a solar cell. From the sunlight, it generates electricity. So, the solar panels are made up of solar cells that again for the production of electricity, or we can say generation of electricity. This is a very economical, efficient process and environment friendly, but the initial cost can be high. But the solar cells are a very good and useful substitute electricity generating method. used in making computer equipment. Again, students, you all know computer chips and computer equipment are mostly made from electronic devices. And transistors and diodes are electronic devices. So, therefore, silicon is useful in making computer equipment. So, that is what you need to know about silicon. Now, we will look at another type of metalloid, boron. Boron is another type of metalloid. Pure boron occurs as black crystalline solid. So, if you take the boron, it is a black color crystalline solid. Melting point is 2200 degrees Celsius. That is a very high value. Therefore, it is a solid at room temperature and it can withstand very high temperatures without melting. Density 3300 kilogram per meter cube. That is also a very high density. Its reactivity is relatively low. So, it does not react very quickly. Therefore, boron is very useful to us. We will now discuss the uses of boron. Uses of boron used in welding metals. Students, you know what welding metals is. You use the oxyacetylene flame, a very bright flame, to paste or fix metal structures together. That process of fusing metal objects together is known as welding. For that, we use boron element. Used in making skin cream. So, boron is useful in making skin cream, which is applied for the protection of the skin. Used in making glass that can be heated to high temperatures. If you look at the glassware in the lab, you might have read the word borosilicates. So, borosilicates are a type of material that is used to make laboratory glassware, which can withstand very high temperatures. So, that is a use of boron in the laboratory. So, students, I hope you all got a very good understanding of what metalloids are. Initially, we discussed metals and examples, non-metals and the examples. Now, we have discussed different types of metalloids and their uses. With this, you would have got a very good understanding about different types of elements that exist in nature, their properties, both physical and chemical, and the uses of these elements to us. Now, students, we will discuss the nature of oxides of different elements. Acidic, basic, and amphoteric nature of oxides. When we say acidic, now qualitatively we can explain this. If you look at the chemical substances available in your household, any material or any substance that is edible that you can eat, if it contains a sour taste, for example, lime juice, orange juice, tamarind, these are all acidic in nature. Whereas basic substances are slimy. When you mix it or dissolve it in water, if you feel a slimy nature, that means they have a basic nature, or that is a basic substance. And amphoteric means, ampho means both types. any material that can show both acidic and basic nature is known as amphoteric nature. So on one side we have the acidic property, opposite of that we have the basic property, and in between, when elements show both properties, we call them amphoteric. And when we discussed before, you can remember, students, the metals formed basic oxides and the non-metals formed acidic oxide. Now we will see how this acidic, basic, amphoteric nature varies across the period from left to right. So as an example, we will consider the elements in the third period. Try to recollect the periodic table, the first 20 elements. Hydrogen and helium belong to the first period. Starting from lithium up to neon, it is the second period of elements. So what is the first element in the third period? You can remember, students? Yes, it is sodium. So we have sodium, then we have magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. Have we included all the elements in the third period? No. We have left out argon. Why? Because argon is a noble gas. It does not react well. It has very low reactivity. Therefore, it doesn't form oxides. So, the elements from group 1 to group 7, they can react with oxygen and form oxides. So, you will have to know the chemical formula of the oxide. After this, you will learn how to write chemical formulae. Now, I will write down the formulae of these different oxides. Sodium forms Na2O, sodium oxide. Then magnesium forms MgO, magnesium oxide, MgO. Aluminium forms Al2O3. Silicon, SiO2. Phosphorus, P2O5. Sulphur, SO3. And chlorine, Cl2O7. So, students, you have to remember the chemical formulae of these different oxides. Sodium oxide, Na2O, magnesium oxide, MgO, Al2O3 is aluminium oxide, SiO2 is silicon dioxide, P2O5 is phosphorus oxide, or we call it phosphorus pentoxide, SO3 sulfur trioxide, and Cl2O7 oxide of chlorine. Now these oxides show different acidic, basic and amphoteric properties. If we take the oxide of sodium, it is a very strong base. It is a strong base. Whereas magnesium oxide is a weak base. It is a weak base. Aluminium oxide, Al2O3, has the special property amphoteric nature. It has properties of acids and bases both. Therefore, aluminium oxide is amphoteric. Amphoteric. Silicon dioxide is weakly, very weakly acidic. So, we can write this as very weak acid. P2O5 is a weak acid. Sulfur trioxide is a strong acid. This is a strong acid. Whereas Cl2O7, oxide of chlorine, is a very strong acid. So, very strong acid. So, you can get a good understanding, students. We have the metals which are basic. They form basic oxide. So, strong base, weak base. Although aluminium is a metal, it forms amphoteric oxide. And all these, silicon is a metalloid, phosphorus, sulfur, chlorine are all non-metals. And non-metals form acidic oxides. And as you can see, when we go from left to right along the period, the basic nature decreases and the acidic nature increases. So, along the period, from left to right, the basic nature of the oxides decreases and the acidic nature of the oxides increases. So, that is how the properties of the oxides change across a period from left to right. So, as an example, we have taken the elements in period 3, starting from sodium up to chlorine. And as I said before, we do not consider group 8 or group 0, which are noble gases, because they normally don't form oxide. Okay, students, with this, we have come to the end of the discussion on different types of elements, metals, non-metals and metalloids, and the nature of their oxides. Now, we will go on to the next topic, chemical formulae. Chemical formulae. So, as you know, students, elements combine together and form chemical bonds. Thus, they form compounds. The formula of these compounds is known as chemical formula. So, if it is for one compound, we say its chemical formula. Many compounds, chemical formulae. So, now we will see how we can come up with these chemical formulae and how to write chemical formulae. Before I go to that, I will explain what this term is. Valency. If we take an atom of an element, it has a certain ability to combine with another element. For example, if we take oxygen, when hydrogen and oxygen combine, we get water. In that, one oxygen atom can combine with 2 hydrogen atoms. So, the ability of oxygen to combine is considered as 2 because it can combine with 2 hydrogen atoms. So, to define valency, we can say the ability of an atom of an element to combine with an atom of another element. So, I will define valency, ability of an atom of an element to combine with another atom is known as valency. So, for example, if we take water, that is hydrogen and oxygen, where there are two hydrogens, H2O. So, the ability of oxygen to combine is equal to 2. Therefore, we say valency of oxygen equals 2. And always this valency is considered in relation to hydrogen. How many hydrogen atoms can this atom of an element combine with? So, oxygen can combine with 2 hydrogens. Therefore, the valency of oxygen is 2. The same way, if we take nitrogen, nitrogen can another example. Nitrogen can combine with 3 hydrogens. Therefore, valency of nitrogen is 3. This is how we derive valency value. So, always valency is considered relative to hydrogen atom. How many hydrogen atoms can it combine with? And also, students, you all know, for the convenience of identifying elements, we use standard symbols. And these symbols have the first letter capital. If the symbol has more than one letter, that is 2 letters, first letter has to be capital, the second letter is simple. So, all the elements are given symbols. And what I have already written here, hydrogen H, oxygen O, nitrogen N, and again hydrogen H. All these are the standard symbols of these elements. Similarly, there are standard symbols for all the elements. For example, if we take the standard symbols, for example, we will look at a few standard symbols. The standard symbol of calcium is capital C, simple A. Say, standard symbol of iron is Fe. Standard symbol of chlorine is Cl. So, students, this is something that is very familiar to you all. You know the first 20 elements in order. You know the standard symbols of these elements. And also, you know the standard symbols of many other elements. Now, we will see how we can identify the valency of these different elements. Here is a periodic table under writing formulae using valency. We have already discussed what valency is. The ability of an atom of an element to combine with an atom of another element. And this is derived relative to hydrogen. But there is a relationship between the electronic configuration and the valency. And also, some elements can have more than one valency. So here, when we talk about valency, there are some elements with many valencies. So before going to that, we will see how we can relate the valency to the elements in the periodic table. For example, I said oxygen has valency 2. We will go back to the atomic number of oxygen. If we take oxygen, oxygen has atomic number 8. So the electronic configuration is 2, 6. And you know that the noble gases, since they have the maximum number of electrons in their energy levels, they are very stable. Now, if you look at the number of electrons in the valence shell, we discussed before that the last shell that contains electrons is known as valence shell. So, the number of valence electrons in the valence shell is 6. If this 6 gets another 2 electrons, then it will have a complete second energy level. And the valency of oxygen is also 2. So, mainly these atoms combine in order to become stable. So, they combine in a ratio so that they can get the maximum number of electrons in their valence shell. So, if you add 2 electrons to this, it will become 2, 8. This is a stable configuration. Stable noble gas electronic configuration. So, different elements have different number of valence electrons in their valence shell. So, sometimes it's easy for an atom to lose an electron and get this stable configuration. Sometimes it's easy for an element to obtain an electron, or else they might share electrons in order to get this complete configuration. So, for example, if we take sodium, sodium has 11 electrons, 2, 8, 1. Since it has only 1 electron, it's easy for sodium to lose this 1 electron. So, can be lost. The same way, if we look at another type of element, say chlorine, it has 17, 2, 8, 7. Now here it has 7 electrons. Rather than losing those 7 electrons, it's easy for chlorine to gain 1 electron. So here chlorine will try to take up 1 electron. So by gaining 1 electron, it can achieve that 8 configuration, 2, 8, 8 stable configuration. Whereas there are elements like carbon. It has 4 electrons. So we will look at the electronic configuration of carbon. Carbon is 6. It has 2, 4. It will not want to either take up 4 electrons or lose 4 electrons. Therefore, it prefers to share 4 electrons. So, here carbon will share 4 electrons. It will share 4 electrons. So, elements form bonds or compounds by either losing, gaining or sharing electrons. And the number of electrons they either lose, gain or share is equal to the valency of that element. And this valency directly depends on the group number of the element. If we look at this periodic table, you can see group 1, hydrogen, lithium, sodium, potassium. All of them have only 1 electron in their valence shell. Therefore, it's easy for them to lose 1 electron. So, the valency of group 1 will be 1. I'm writing the valency value. If you take group 2, beryllium, magnesium, calcium, they have 2 electrons in their valence shell. So, easy to lose 2 electrons. Therefore, valency will be 2. Group 3, boron and aluminium. They can either lose or share 3 electrons. So, the valency is 3. Valency 3. Carbon, as we discussed, and silicon, they have 4 electrons. It's easy for them to share the 4 electrons. So, their valency will be 4. Then we come to group 5, nitrogen and phosphorus. Now, nitrogen and phosphorus have 5 electrons. What is easy? Losing 5 or gaining 3, or at least sharing 3. Yes, it's easy for nitrogen and phosphorus to share or gain 3 electrons, then losing 5 electrons. So, therefore, the valency becomes 3 again. 8 minus the group number. So, here we can write it as 8 minus group number 5, that is equal to 3. The same way, group 6, oxygen and sulphur have 6 electrons. It's easy for them to gain or share 2 electrons, then losing 6 electrons. So, again 8 minus 6. 8 minus 6. So, it becomes 2. By now, you would have guessed the valency of group 7. What is it, students? 8 minus 7. Valency 1. Because group 7 has 7 electrons in their valence shell, easy to gain 1 electron and form a negative ion. Yes. So, the valency 1, 2, 3, 4, 3, 2, 1. Then we come to group 8. Group 8 is known as group 0. Now you can see the meaning. 8 minus 8, 0. Why? The noble gases, that is group 8 elements, have complete energy levels, complete valence shells. Therefore, they are not reactive, they don't form compounds, and they show 0 valency. So, the valency of group 8 is 0. That is the reason we call them as group 8 or group 0. So, this is the relationship. Going across the period, from left to right, starting from group 1, 1, 2, 3, 4, 3, 2, 1 and 0 for group 8. This is how we get the valency for different elements. And you have to remember, students, some elements. For example, phosphorus, sulphur and chlorine. They can have more than one valencies. There are many elements with more than one valencies, but for y'all, if you remember these three elements, phosphorus, sulphur and chlorine. According to the group number, phosphorus will have valency 3. At the same time, phosphorus can have valency 5. So, phosphorus has valency 3 and 5. Similarly, sulphur, because it's in group 6, it has valency 2. But it can have valency 6. So, chlorine, because it belongs to group 7, it has valency 1 and also it can show valency 7. So, chlorine has valency 1 and valency 7. So, these are elements that have more than one valencies. If you look at this, Cl2O7 was the oxide of chlorine. There, O7 comes because chlorine has valency 7. So, these are the elements that you need to remember as having more than one valencies. With this in mind, I hope you have understood what valency is and how we can relate the valency to the position of elements in the periodic table. Now, we will summarize these valencies again. Valencies of the elements from atomic numbers 1 to 20. You have the atomic number here, the element, symbol and the valency. By looking at it, you can remember these valency values. Atomic number 1, hydrogen, H, valency 1 because it's in group 1. Atomic number 2, helium, He, valency 0 because it is in group 8 or group 0. 3, lithium, Li, again valency 1. Beryllium, atomic number 4, valency 2. Boron, atomic number 3, valency 3. Then we have carbon, atomic number 6, valency 4. 7, nitrogen, valency 3. 8, oxygen, valency 2. And 9, fluorine, valency 1. Again, neon, atomic number 10, it is a noble gas, valency 0. So, here you can see across the period from left to right, according to the group number 1, 2, 3, 4, then 8 minus group number 3, 2, 1, 0. This is how the valency values change. These are the first 10 elements. We will look at the next 10 elements. Starting from sodium. Atomic number 11, group 1. So, sodium, valency 1. 12, magnesium, valency 2. 13, aluminium, valency 3. 14, silicon, valency 4. Then you can see 15, phosphorus, again valency 3. Sulphur, S, group 6, valency 2. Then chlorine, group 7, valency 1. And argon, group 0, valency 0. So here also you can see the pattern. 1, 2, 3, 4, 3, 2, 1, 0. In addition to that, you can see the additional valencies. Phosphorus 5, same as group number. Sulphur 6, same as group number. Chlorine 7, same as group number. So, if these have more than one valency, you might wonder why the other elements, say for example, nitrogen, which also belongs to group 5, does it have valency 5? No, it does not have valency 5. There is a reason for that, students, but it is more than our topic. So, therefore, remember that only these three, not the elements above these, have more than one valencies. Only phosphorus, sulphur, chlorine for our syllabus has more than one valencies. Then again, coming to the 19th and 20th elements, potassium and calcium, K is the symbol, Ca is the symbol. Again, you know 1 and 2 because they go to the 4th period. So, like this, you can relate the valency of elements to the position in the periodic table, and also from the atomic number, you can come to the valency value. So, now you have a good understanding of what valency is. Now, we will see how atoms of elements combine and form the compounds based on valency. So, here we are going to look at how chemical formulae are written. I will read this first, then explain it to you. What is done in writing the chemical formula of a compound is connecting the atoms so that their combining powers become equal. This is done by exchanging the valencies of the two elements and writing them at the bottom end on the right hand side of the respective symbol. So, in order to write the chemical formula, you have to know the symbol of elements. For example, if you are supposed to write the chemical formula of the compound formed between hydrogen and oxygen. Obviously, you know that it is water and you know the chemical formula. Now, we will explain this using water. Say water is formed between water is formed of hydrogen and oxygen. So, the constituent elements are hydrogen and oxygen. We have to write the standard symbols. Then what do we write? We write the valency value of each element below that in the next line. So, hydrogen, because it belongs to group 1, you can remember valency 1. Oxygen, group 6, valency 2. So, the valency 2 is written here. That is the first part, right? This is done by exchanging the valencies of two elements. Then what do? We exchange. Give the valency of oxygen to hydrogen and valency of hydrogen to oxygen. Then you will get the formula as H2O1. And when you get the value 1, you don't need to write it. So, no need to to write. So therefore, we rewrite this formula as H2O. When you have a formula like H2O1, when you write the symbol of the atom itself, it's understood that there is one atom. So we don't have to denote it as 1. So this is the formula of water. From this, you can understand this step. Writing them at the bottom end on the right hand side of the respective symbol. So after exchanging, we write it at the bottom right hand side of the symbol, H2O, and no need to write 1, because from having one atom, it is understood there is only one atom. Only if it is more than 1, we have to give the number. We will look at another example, the compound between nitrogen and hydrogen. Nitrogen is in group 5, the valency is 3. So we write the valency there. And hydrogen has valency 1. We have to exchange the valencies. So it will become NH, N1, H3. What can we do after this? We can omit this 1. So the formula will become NH3. Once you are used to writing chemical formulae, you can skip this step. From here, you can directly write that step because you don't have to show 1. So this is the chemical formula of the compound ammonia formed between nitrogen and hydrogen. Water, so this is water. Then we have ammonia. And then we can have another example, the compound formed between carbon and hydrogen. Carbon has valency. It can share 4 electrons. Hydrogen has valency 1. And when we exchange the valencies, you will get the formula as CH4. And this is the compound methane. So students, now we have written the chemical formulae of 3 compounds, water, ammonia and methane. So likewise, you should practice and write different formulae for different compounds. We will do an example writing the chemical formula of the compound formed between magnesium and oxygen. So let's say magnesium has the symbol Mg, oxygen is O. Here the valency of magnesium is 2, oxygen is also 2. Magnesium is in group 2, oxygen is in group 6. And when we exchange the valencies, we get Mg2O2. Here you can see both the values are the same, 2 and 2. Therefore, we can rewrite the chemical formula as MgO, omitting the 2 values because they are equal. The same goes for compound calcium oxide. This is magnesium oxide. When we write calcium and oxygen, the compound formed between the 2, we have valency 2, 2. And when we exchange, it becomes Ca2O2. O2, we can rewrite it as CaO, omitting the valency 2. We will look at another example. Let's say the compound formed between sodium and oxygen. Sodium belongs to group 1, valency 1, oxygen 2. So, when we exchange the valencies, we get Na2O. That is the chemical formula of sodium oxide. One more example. The compound formed between aluminium and oxygen. What is the group of aluminium? Yes, it's group 3. What is the valency of aluminium? 3. So, you all know the valency of aluminium is 3, oxygen is 2. So, when we exchange the 2 valency value, we get the formula as Al2O3. So, that is the chemical formula of aluminium oxide. So, students, now you have a good understanding as to how we are writing chemical formulae of compounds formed between atoms of different elements. So, in all these examples, we had only 2 types of atoms of elements because it was between 2 elements only. But if you can remember, you all know the chemical formula of sodium hydroxide, NaOH. There are 3 different elements. Sulfuric acid, H2SO4, hydrogen, sulfur, oxygen. Again atoms of 3 different elements. So that means more than one elements can combine and form compounds. In doing that, there are molecules which have charges. Now we will look at such examples. Polyatomic ion. A new name, polyatomic ion, new to you all, or radicals. So this polyatomic ion is an orderly arranged group of atoms of elements with a charge. So if there is a molecule, in that there will be atoms arranged in an orderly manner. But if that molecule has a charge, then we call it polyatomic ion. So far, we have discussed ions of elements with positive and negative charges. Now here, more than one type of atoms. That is why we say polyatomic ion. Polyatomic ions. For example, if you take the ion OH minus, oxygen and hydrogen are arranged in an orderly manner and it has a charge. So this is a polyatomic ion. We call this the hydroxide ion. Similarly, if we have SO4 2 minus, this is known as a sulfate ion. You must be wondering, is it only negative ions? No, there are positive polyatomic ions as well. For example, if we take NH4, it has a positive charge. Remember students, NH3 is ammonia. That is different. So you have to remember NH3 is ammonia this is a molecule or a neutral compound. But when you have NH4 plus, then we call it ammonium ion. So make sure you remember them separately and clearly. You should not confuse the two. This is a molecule, a compound, and this is ammonium ion, NH4 plus, which is a polyatomic ion or a radical. Now these polyatomic ions or radicals can form bonds. And when they form bonds and form compounds, they also need to combine in a certain manner. For that, they need to have a valency. Yes, the valency of these polyatomic ions is their charge, the number of charges, not the type of charge. It can be negative or positive, does not matter, but the number of charges. There is one negative charge, so the valency is 1. Here, if we take sulphate, SO4 2 minus. So the valency is the number of charges, that is 2. Again, for ammonium ion, there is only one positive charge. So valency of ammonium ion is 1. We will look at another example, phosphate ion. It is written as PO4 3 minus. So here the phosphate ion has 3 minus charges. So that means the valency is equal to 3. So students, now you can understand very well that there are different types of polyatomic ions. They can be positive ions or negative ions. And the valency of these ions is equal to the number of charges. So I will write this down. Valency equals number of charges only. We do not need to consider the sign of the charge. So like this, you can remember the valency of different polyatomic ions. Now we will look at some more examples for polyatomic ions. You can look at this table. The name of the radical is given to you. You will have to remember the names, the chemical formula, and the valency of all these polyatomic ions. So we will start with the first polyatomic ion, the ammonium ion. I have discussed this before. What is the chemical formula? Yes, it is NH4 plus. So then what will be the valency? Valency 1. Hydronium ion. Hydronium ion means it is H3O plus. H3O plus is hydronium ion. So 1 plus, valency 1. The third polyatomic ion or radical is nitrate. Nitrate is NO3 minus. So 1 minus charge, valency 1. Next we have hydrogen carbonate or bicarbonate ion. This is written as HCO3 minus. So again the valency is 1. We have already discussed hydroxide ion. Remember the formula? Yes, it is OH minus. So the valency will be 1. Then we have the next type, permanganate ion. Permanganate is M, N is manganese, MnO4 minus. So therefore the valency is 1. MnO4 minus is permanganate and the valency is 1. Then we have hydrogen sulfate or bisulfate. That is HSO4 minus. So the valency of that is also 1. Then we have another radical, chromate. Chromate has the formula CrO4 2 minus. Cr is chromium with oxygen. It's CrO4 2 minus. Since it has 2 negative charges, the valency is 2. Then we have dichromate. Dichromate is Cr2O7 2 minus. Again valency 2. Then we have sulfate. SO4 2 minus. Sulfate SO4 2 minus. So that is also another polyatomic ion, sulfate. Then the last 2 ions we have, carbonate is CO3 2 minus. Because the charge is 2, the valency is also 2. And finally, phosphate. I have already shown phosphate to you all. Try to remember the chemical formula. Yes, it is PO4 3 minus. Since it has 3 negative charges, valency 3. So now students, you can see the different chemical formulae of the different radicals or the polyatomic ions, and you can see that the number of charges in each polyatomic ion becomes the valency of that ion. Now we will see how we can write chemical formulae using these polyatomic ions. Writing formulae for compounds with polyatomic ions. We will take an example, sodium nitrate. So when you are told to write the chemical formulae of a compound, first you need to identify whether it is an atom or a molecular ion that is present in the molecule. Here you can see sodium is an element, sodium metal, and nitrate, you have to remember the chemical formulae. It is a radical NO3 minus. So then you have to remember the valency values. Sodium is 1, nitrate, since it has 1 negative charge, the valency is 1. Then what do? We exchange the valencies. And when we write the sodium metal first, the sodium atom, and next to that we write NO3. And as you know, 1 and 1 need not be shown here. So we just leave it as NaNO3, sodium nitrate. We will look at another example, magnesium nitrate. magnesium nitrate. Again, it is a compound formed between magnesium and nitrate ion, NO3 minus ion. What are the valencies? Yes, magnesium has 2 and nitrate has 1. Why? It has 1 negative charge. What is the next step? We need to exchange the valencies. And when we rewrite Mg, we don't need to write 1. Now we have to write NO3, that is the nitrate ion, and 2 of those. If we just write the 2 next to 3, it will either look like 32, it will not be clear. So we have to make sure that we put parentheses, brackets like this around polyatomic ions when there are more than 1 polyatomic ions in the molecule. Here there was only 1 nitrate, we need not use parentheses. But here there are 2 nitrate molecules, so we have to use parentheses and then write the 2 there. So this is the chemical formula of magnesium nitrate. We will look at another example, say sodium sulphate. Sodium sulphate, sodium is Na, sulphate is SO4 2 minus. The valency of sodium and sulphate, you remember? Yes, sodium is 1, sulphate is 2. Then we have to exchange the valencies. Then what do we get? Na2. Here no problem. You can directly write the valency 2 of sulphate. And then we have SO4, it's only 1. We need not put parentheses, we can just leave it as it is. So this is sodium sulphate. We will do one more example. Calcium phosphate. Calcium is Ca. What is the chemical formula of phosphate? Yes, it is PO4 3 minus. So what are the valencies? Calcium is 2, phosphate 3. We exchange the valencies. How are we to write? Ca3, because the valency of phosphate is 3. Then we have PO4, but PO4 has to be 2. Then what do we have to do? We have to put parentheses and then write the 2 there. So this is the formula of calcium phosphate. So students, we have looked at different examples how to write chemical formula for compounds with only elements and with elements as well as radicals. So you have a very good understanding as to how you are supposed to write the chemical formulae. You have to remember the valencies. You have to remember the formulae of the different radicals or the polyatomic ions. Then you will know the valencies. Then you know the way of writing the chemical formula. So with these students, we have come to the end of the lesson. We discussed many different topics. We started off with elements, the structure of atoms, then the periodic tables, then we discussed patterns seen in periodic tables. Thereafter, we discuss the different types of elements, metals, non-metals, metalloids, and examples. And finally, we discuss how to write chemical formulae. You have to keep on practicing how to write chemical formulae. There are more examples in the exercise. Then also we can practice. At the same time, you yourself can write different chemical formulae. But after writing, make sure to check it with the book to see whether you have written the polyatomic ions or the radicals correctly and the valencies correctly. Now with that, we will go on to the summary of the lesson. Summary. Atoms are the building units of matter. We started off with that. Atoms are formed by the three main subatomic particles: electrons, protons, and neutrons. At different times, different models were proposed for the structure of the atom. So, you know, basically atom is the building unit. It's made up of electrons, protons, and neutrons, and there were different models that were proposed. And out of those, Ernest Rutherford presented the planetary model for the atom. Another name is the nuclear model. And then Niels Bohr further illustrated, or Niels Bohr stated that the electrons move in definite paths or shells around the positively charged nucleus. So that is the elaborated and most accepted model of atoms. Nucleus in the center with the positive protons and the neutral neutrons, electrons going around in energy levels or shells. The modern periodic table is based on the patterns observed in the properties of elements when they are arranged in the ascending order of their atomic number. So, to make it easy to identify and learn about elements, the periodic table has been arranged or classified. So, this is based on the ascending order of atomic number and also the electronic configuration. Elements are divided into groups according to the number of electrons in the outermost shell or the energy level. That is what we call as valence electrons or valence shell. Electrons present in the valence shell. So that is related to the group number. And elements are divided into periods in accordance with the number of shells or energy levels that contain electrons in their atoms. So we look at the number of energy levels and identify the period of the element. The minimum amount of energy required to remove an electron from a gaseous atom of an element to form a unipositive ion in the gaseous state is known as its first ionization energy. This is the definition for the first ionization energy. You have to remember that. To continue, a regular pattern can be seen in the variation of the first ionization energy. Variation of the first ionization energy of elements across a period from left to right. You can remember the zigzag pattern. 1, 2, 3, 4, 5, 6, 7 and the highest 8. When you go to the next period, again it decreases and shows the same regular pattern. Down the group, the first ionization energy of elements decreases. Why? The size of atoms increases because the number of energy levels that contain electrons increases. When an atom is joined to another atom by a covalent bond, the ability of that atom to attract electrons in the bond towards itself is called electronegativity. We have discussed electronegativity very well, and in that you remember the electronegativity increases from group 1 to 7, but group 8 is not considered for electronegativity. Why? Because they are noble gases and they do not involve in bonding or forming compounds. The electronegativity of elements increases across a period and decreases down a group. Across a period from left to right, acidity of oxides formed by the elements increases. So, acidity increases, basicity decreases. Metallic oxides are basic. Non-metallic oxides are acidic. What is aluminium oxide? Yes, it is amphoteric. Across a period from left to right, the metallic properties of elements decreases and the non-metallic property increases. Group 1 and 2 are good metals. Group 3, aluminium is a metal, but boron is a metalloid. But when you go to group 5, 6, 7 or even starting from 4 carbon, those are all non-metals. Boron and silicon are metalloids. So you can see this change. Based on the physical and chemical properties, elements can be classified as metals, non-metals and metalloids. We have discussed that in detail and we discussed a few examples for these different types of elements. Majority of the elements so far identified are metals. More than 80 of the elements present in the periodic table are metals. So, majority of the elements are metals. This is what we have discussed in this lesson. So, students, I hope you have understood the lesson well and you will keep on reading it again and again, understanding it, understand the pattern and learn to write chemical formulae. You can try all the questions in your exercise book and there are some more additional questions that I'll be discussing with you. You can do that as well.